Alright, in this video today we're going to take some time to review back through that equation you practiced yesterday, which took a look at the relationship that existed between frequency and wavelength. And then we're going to take a look at another equation that allows us to relate frequency and wavelength and energy together. So starting with the relationship you learned yesterday, you saw that for waves that are part of the electromagnetic radiation spectrum, we have this equation right here where our speed of light, which speed of light is a constant and is always going to be 3 times 10 to the power of 8 meters per second. So our speed of light is equal to wavelength times frequency. So what that means is if we know either the wavelength or the frequency, it's possible for us to solve for the other. And if we look down here in our problem, we can see that this time it's asking us to find the wavelength and it provides us with a frequency. So our frequency here is 5.25 times 10 to the power of 15 hertz. So plugging information that I know then into this equation that I have here, we can see that my speed of light, which is 3 times 10 to the power of 8 meters per second, is going to be equal to wavelength, that's the one that I'm looking for, there's my lambda, times frequency. So multiplying by 5.25 times 10 to the power of 15 hertz. And remember, hertz is basically 1 over second. Right, so at this point I'm ready to solve using algebra because I'm multiplying here. I'm going to go ahead and divide by my numerical value, 5.25 times 10 to the power of 15, 1 over seconds. That's going to cause these both to cancel, leaving me with just wavelength over here. And since I divided by that number on this side, in order to keep things equal, I need to divide by it over here as well. So I'm going to go ahead and divide by 5.25 times 10 to the power of 15, 1 over seconds. Taking a look at my units, I see I have over seconds in both of these, so these are going to cancel, leaving me with units of meters. So that's a good, because that's how I can measure things like length, wavelength. And then I'm going to go ahead and grab my calculator, and plugging this in, we have 3 times 10 to the power of 8 divided by 5.25 times 10 to the power of 15. And my calculator then is telling me that my wavelength is 5.71 times 10 to the power of negative 8 meters. And so that would be the wavelength then that we would be looking at here. If we take a look at that picture of that spectrum, we can actually kind of check to see. You can see down here you have things like frequency and wavelength, and so we can use those to kind of help us out. So we saw that my frequency was 5.25 times 10 to the power of 15 hertz. So that's, if we take a look here, here's 14, here's 16, so it's going to be somewhere here in the middle, which means my answer is going to fall somewhere about here. And then we can also see that I wanted to get 5.71 times 10 to the power of negative 8, and I know these numbers are really small, but here's my negative 8, so we can see that we would be probably somewhere pretty close to that value as well. So we can always kind of use this graph as well to check to make sure that my numbers are making sense. So that's hopefully what you guys are feeling pretty comfortable with, having gone through and practiced yesterday. Today we're going to take a look at this new equation. So if we know things like frequency or wavelength, it's possible for us to solve for the energy that wavelength has. And ultimately this is really what we care about, because this is what Bohr is going to end up using as his evidence to prove where electrons are. And remember, that's the whole goal of what we're looking at. Where are the electrons and what evidence do we have to support that? And so being able to look at energy is what it is that we ultimately want. So the equation that we use then to solve for energy is as follows. Energy, E, is equal to Planck's constant, which is h, and it's a constant, so it's always going to be 6.626 times 10 to the negative 34th joules times seconds, multiplied by frequency. Right? And we can solve for frequency. We know that equation of C is equal to wavelength times frequency. So if I solve for frequency, I'm going to have to divide both sides by wavelength. And that leaves me with the equation of frequency is equal to the speed of light divided by wavelength. So I can plug this into frequency, and that gives me my second equation. So note that these two equations are equal to each other. All right, the second equation is going to be Planck's constant times the speed of light, all divided by wavelength. And so you would pick the equation that would be needed based upon whether or not you were provided with frequency or wavelength for a specific wave. So taking a look at a problem here, we can see this time it wants me to calculate the electromagnetic radiation. This is my energy. All right, so it's asking me to calculate the energy that is associated with a wave that has a wavelength of 2.3 times 10 to the negative 5 meters. So because I'm given wavelength, I'm going to end up using the second equation since this one has wavelength present in it. So looking through and plugging in the values that I know, I want to calculate energy. So energy is going to stay E, and that's going to be equal to, Planck's constant, H, so 6.626 times 10 to the negative 34th joules times seconds. And I'm going to multiply that by speed of light. Again, remember speed of light is 3 times 10 to the power of 8 meters per second. And then I'm going to divide all of this by wavelength. So dividing by wavelength, I have 2.3 times 10 to the negative 5 meters. Now the first thing I want to do is take a look at my units. So we can see here I have things like seconds on the bottom and seconds here, so those are going to cancel. I also have meters on the top and meters on the bottom, so those are going to cancel. And I'm left then with joules. And joules is a way for me to measure energy, so that's good. So I have units that lead me to what it is that I'm trying to solve for. So now I'm ready to grab my calculator. Now, I strongly recommend that as you guys are entering these types of equations into your calculator, you're using scientific notation so that you don't have to worry about order of operations. If you choose to enter in something like 2.3 times 10 caret negative 5, make sure that you're putting those kinds of things into parentheses so your calculator divides where you want it to divide. But if you plug this all into your calculator, you should end up with, let me get you a number here. You should end up with 8.64 times 10 to the negative 21 joules. And that would be the energy that would be associated with that photon that has a wavelength of 2.3 times 10 to the negative 5 meters. Now if we take a look here, coming back to our electromagnetic spectrum again, we can kind of think about this spectrum in terms of frequencies, in terms of wavelengths, and now as well in terms of energy. So if we go back to what we were talking about yesterday, when we talk about things like wavelengths and frequencies, we know that those things are inversely related. So over here we have things like radio waves and radar, and you can see based upon the picture that these kinds of things have very long wavelengths. All right, so they're going to have long wavelengths. In other words, this number is very big. All right, and we know that wavelength and frequency are inversely related. So if we have long wavelengths or big wavelengths, that means we're going to have very small frequencies. And that makes sense, right? There's not going to be a lot of waves that are being repeated when they're this big over a set period of time. As opposed to over here, when we come to the edge that has things like gamma rays, this time our wavelength is very short, right? So this time we have those short wavelengths, or in other words, we have very small numbers, which means our frequency is inversely related. We're going to have very, very large frequencies. We have lots of waves being completed in that same amount of time that we have very few waves being completed over here. Now we can add energies into this as well. When you have something that has very long waves, we have things that have very small energies or low energies associated with that. All right, so we can say this side has low energy versus over here when you have very short wavelengths, you have a very, very high frequency, you also have to have very large energies. So this side is going to have large or big energies associated with it. Right? And so we can also think about colors of light in the same way. So our spectrum is split up into our rainbow of colors, where over here we have our reds leading into oranges and yellows, and this is going to have those smaller wavelengths, those larger wavelengths, which means they have smaller frequencies and lower energy associated with them, versus over here on this side, as we move more into our blues and purples and indigos, we have much shorter wavelengths, right? Much smaller wavelengths, meaning we have larger frequencies and a lot higher energy associated with that. So different colors of light have different energies associated with them, and that becomes really important as we move into our next topic. So next week we'll take some time to go into the lab and actually look at different colors of light that different elements can produce, and we're going to use that along with this understanding to finally answer that question of how exactly do we know where these electrons are located at. Now that you guys hopefully understand how to calculate things like energy, you're ready to do your next WebAssign. I believe it's called Waves and Photons, and it's going to have you practice calculating energies and reading this chart and figuring out wavelengths and types of waves and things like that. Best of luck. Let me know if you have questions.